So this video is going to be on complex numbers. Now, when we have simplified radical expressions, and if the radicand was negative, we always said, oh, can't do it, because to have something like the square root of -4, there is no number times itself that gives us a negative, because a negative times a negative is a positive number. And so there is no number that multiplied by itself would give me a -4, so we couldn't take the square root. So in the past, we would have said something like, oh, there's no real solution to this, no real answer, you can't do it. Well, what we're finding out with complex numbers is that that is no longer going to be the case. We can simplify that by introducing the imaginary number I. Now, I is being called an imaginary number, not because it's make-believe. The connotation for imaginary, back in the day when they were first coming up with this, is more that it was an image of something. So it's kind of like having that negative from your film when you're taking in the old school cameras, of course, that it's kind of there, but it's not fully developed. That is more of what the complex number does. And it's going to allow us to proceed further in mathematics. It is used in the electrical field a lot, and there are a few other fields in which it comes into. If you go into a higher level of mathematics, you will deal with a little bit more of the I's in a calculus type of problem class here and there. So there are those applications to it there. So we're just going to do some basics with it. First of all, we need to understand what is an imaginary number. And then we're going to go through the operations of adding, subtracting, multiplying, and dividing it. And then learn a little bit more about it. So what happens is when we're in a case like this, the square root of -4, we know that one of our laws of radicals is that I can make a product underneath there. So I'm going to rewrite this as -1 times 4. Means the same thing as -4, it's just written as a product. Then our law of radicals allows us to separate that into two radicals. So we can say, okay, the square root of -1 times the square root of 4. Now the square root of 4, we know what that part is. That's just going to be 2. It's the square root of -1 that causes us to have issues. Because we can, as I stated before, we can take some number times itself, but we can never get a negative. So that square root of -1, that is I, your imaginary number. So I is equal to the square root of -1. But since the square root of -1 causes us an error, we've identified it as I. Now I is going to act a lot like a variable. When we're adding and subtracting, we only add and subtract parts that have I, and the I will come along for the ride. And when multiplying an I times an I will give us an I squared. And we'll talk about that in a little bit too. But so once we have this I in it, we now have what's called a complex number. A complex number is a combination of a real number and an imaginary number. So the standard form of a complex number is A plus BI, where A and B are real numbers that we're used to, any number that you'd like to, and then I is the imaginary. So this is broken, the standard form of a complex number is broken into the real part and the imaginary part. The imaginary part has, imagine that, the imaginary number I. But again, A and B are both real numbers. So it's always going to be in that form, though, of A plus BI. That is a standard form of a complex number. So let's go through the operations of what we would do with complex numbers. First of all, if we add them, well, so this is just like adding polynomials. I have my first complex number in parentheses, and then I have the symbol in between saying I'm adding, and there's the second standard form of my complex number. So I'm just adding two complex numbers together. And in that case, we just do exactly as we do with polynomials. We add like terms. So my like term here is an 8 and a -5. So 8 plus -5 is 3. And then we add the imaginary parts. negative 3i plus 6i would give me a positive 3i. I can't combine the 3 with the 3i because, once again, those are not like terms. The 3i has an I, and that first 3 does not. So that would be my final answer of adding. To subtract, it's just like subtracting polynomials. But remember our trick when we subtracted polynomials. To make sure that we don't screw up our signs, we change the subtraction to addition and then make it negative on the outside. Now that negative on the outside, remember, is a negative 1 that has to be distributed in. So the first step here is to distribute in that negative 1 into the second set of parentheses. All that does is it changes our signs. Negative 1 times a negative 6 is going to make it a positive 6. Negative 1 times the positive 7i will make it a negative 7i. And then again, we go back and we combine our like terms. So I have the real part here, 3 plus 6 is 9. And the imaginary part, negative 4i, negative 7i, is a negative 11i. Because those were both negatives. When adding two negatives, you add and keep the negative sign. And again, we can't go any further. Your answer is going to be in standard form of a complex number. Real number first, real portion first, imaginary part second. Multiplying. Multiplying is going to be very similar. We'll go through a few different examples of multiplying. Now in this first one, it's 2i times 3i. But again, the 2 is not married to the I, and the 3 is not married to the other I. So when multiplying, remember the order of multiplication, we can switch that around however we want. So I'm going to do the 2 times the 3 because those are both real numbers that we can multiply together, and we get 6. And then I times I follows the same rule as anything else. If it was x times x, anything times itself is a square. Same thing goes here. I times I is I squared. Now, here's where it's really interesting though. Here's where we do a little bit of a side work. Now, if I is equal to the square root of negative 1, to get I squared means that we are going to square that, right? Whatever you do to one side, I do the same thing to the other side, this equal sign. So that gives me I squared. But on the right side, remember, a square and a square root are inverse operations. They cancel each other out. Just like adding and subtracting cancel each other out. If I have 3 cookies and I take your 2 cookies, I just added to that, I have 5 cookies. Mom saw that I took your 2 cookies, whapped me upside the head. I gave you back your 2 cookies, I'm back to 3. So we have that same operation here. Squares and square roots cancel each other out. So the square cancels with the square root, leaving me with the radicand, the number underneath the radical, which is negative 1. So I squared is no longer an imaginary number. It is a real number. And we don't want to deal with imaginary numbers if we don't have to. Our answers should always be in the lowest set of numbers possible. And a real number is in a lower set than the complex numbers. So I squared will be replaced with its value of negative 1. So this becomes 6 times, make sure that you use parentheses there, because I'm replacing I squared with its value of negative 1, and I need to preserve the fact that I'm multiplying. So make sure that you put that in parentheses. And so then my final answer here ends up being negative 6 when I simplify that. So I squared is equal to negative 1, which means I squared will never be in your answer. Never. Because you always replace it with negative 1. Okay. So here's another one. Let's show our distributive property here. Negative 2i just gets distributed in just like it would if it was negative 2x. We multiply it in. So we're going to get negative 8i, and then a negative times a negative makes it positive. 2 times 6 is 12. I times I is I squared. Aha! Again, I squared will never be in my answer. So this becomes negative 8I plus 12 times negative 1. That's just going to change the sign there. So it's negative 8I minus 12. Now this is not my final answer. And the reason that this is not my final answer is because this is not in standard form. To be in standard form, you have to have the real part first and the imaginary part second. Remember, when you're rewriting it with the real part first, to make sure that you pay attention to your signs. The sign in front of the number goes with the number. The 12 here is negative because of the sign in front of it. So I write negative 12. The 8I is also negative, so it would be minus 8I. That would be your final answer or simplification for that distributive property. Doing some more multiplying, let's do a complex number times a complex number. So we have a binomial or two terms times another binomial. This is the same thing as what we would have done whenever else we are doing any of our multiplying. So what's the case to do here? FOIL. Foiling, foiling, every day. First term, outer, inner, and then last. Can you tell me how to pass this algebra class? And again, the oi of FOIL are like terms, so we can combine those. But then we also have to remember that in the end, we have that I squared. And again, I squared will never be part of our answer. So you have to replace that with that negative 1. And then you have like terms. So our final answer becomes 11 plus 2I. Here's another one. Why are we doing another one as such? Well, more practice, and on top of it, notice the values here. It's 2 plus 3I times 2 minus 3I. So those almost look the same, but the signs in between them are different. So what's going to happen when I FOIL that? Foiling, foiling, every day. First term, outer, inner, and then last. Can you tell me how to pass this algebra class? And the interesting thing, or the neat thing here, is that your middle terms cancel out. Negative 6i and a positive 6i go away. But on the other side over here, I have an I squared. Again, I have to replace the I squared with a negative 1. So interestingly enough, when we multiply these two binomials together, these two complex numbers together, we get a real number. We don't get a complex number. We just get a real number for our answer, or the simplified result. These numbers, the complex number, the standard form of the complex number, when you have the same numbers, but only the sign in between them is different. So it was 2 plus 3i, 2 minus 3i. Those are called conjugates. And when you multiply conjugates together, you get a real number. Okay. That's going to be kind of interesting and helpful when we do some division. When we divide, we're not actually going to be dividing things with i's so much. But they've decided, they being the powers that be, that we cannot have a radical in the denominator. And since I represents the square root of negative 1, square root is a radical, we can't have I in the denominator either. So when we divide, we're actually going to do a process called rationalize the denominator. Now, if I just have a single I in the bottom, like I do in this first example, 1 over 10I, that's going to be easy to simplify because I just need to get an I squared. Remember that I squared was -1. So all I do here is multiply by I. Now, I can't just multiply the bottom by an I because that would change the value. Remember, when we have a fraction, whatever you do to the bottom, you do the same thing to the top because that's going to change what it looks like, but not its value. Because I over I, anything over itself, remember, is 1. And if I take anything times 1, I get anything back. So I'm not changing the value of the 1 over 10I. I'm just going to change what it looks like by multiplying top and bottom by the same thing. In this case, just an I. When I do that, on top, I get I, and on the bottom, I get 10I squared. Well, again, I squared is never in any of my answers, so I replace that with -1. So I end up with I over -10. Now, you could write it like that, but let's face it, it's a little awkward whenever we put a negative in the denominator of a fraction. The other two ways that you could write this is just put the negative in front of the fraction. That just negates the entire fraction. Textbooks like to write it in that fashion. I like to write it on top because somehow it makes more sense to me. -I over 10. Also, when we use the textbook form here, sometimes we get confused and we think the negative's on top and on the bottom, but it's not. I over 10 is one number and it is being negated or being a negative number. Okay. But I like to write it on top, so I think of just the numerator being negative. It reminds me that only one of the numbers is negative. It doesn't matter if it's the top or the bottom. It just has to be one or the other, not both. Okay. So for most of the problems, the division, that's about all that I'm going to have you do, is something of that fashion. However, if we do happen to have a complex number in the denominator, as we do in the second one, we can still get rid of the I. Now, I can't just multiply one term by I. Remember, if I multiplied by I, it would be distributed. And so then the 5 would have an I, and I'd get rid of the I by the 4. So I need to do something else. And that's what brings us to, once again, those conjugates that we just talked about on the previous slide. To get rid of the I in the denominator here, I have to multiply by the conjugate of 5 minus 4i. Again, the conjugate's going to be the same values, but the sign in between is different. I have a minus, so I need a plus. So the conjugate of 5 minus 4i is 5 plus 4i. And again, whatever I do to the bottom, I have to do the same thing to the top. Distributing on both cases now. On top, I'd end up with 15 plus 12i. On the bottom, if I FOIL that out, I'd have 25. And there are rules that you could see that say, oh, this is the shortcut to it. But oftentimes we think that's too many formulas. I don't want to have to remember so many formulas. I know how to FOIL, so I'm just going to FOIL. Plus 20i minus 20i minus 16i squared. Okay. So simplifying that, I have, I should not have distributed through maybe that'll work. So I have 15 plus 12i. On the bottom, those middle terms cancel out. I'm left with 25 minus 16 times that I squared, which again is -1. So that just changes my signs around. Okay, I ran out of space here. So that gives me 15 plus 12i over 25 plus 16, which is going to be 41. Now, you can write your answer like that. To be officially in standard form, though, you should show it as two separate fractions. I personally am okay if you just leave it in this fashion, but I want you to be aware that this is the same thing as 15 over 41 plus 12 over 41i. So you can clearly see the a and the b. A is 15 over 41 and b is 12 over 41 from our form of a plus bi. So to be officially correct, you can write it like that. But I'm all about being as compact as possible, so I'm okay if you leave your answer as we have up here as one ugliness as opposed to two fractions. Okay. Now, let's play around a little bit with I. Now that we know how to add, subtract, multiply, and divide with it, let's look into i's a little bit more. We know that I is equal to that square root of -1. And we just learned now that when I take I squared, I get -1. Because again, the square root of -1 being squared cancels each other out, giving me the -1. So what happens if I have I cubed? Well, thinking about our exponent laws, I cubed can be rewritten as I squared times I. I squared, we just said, was -1. So this is the same thing as -1 times I. Well, we'd write that as -I. So I cubed is just -I. So again, that's a smaller thing than having an exponent of 3. We want to have the smaller exponent as possible. So I cubed would be simplified to a -1. I to the fourth, if we were simplifying that, well, I to the fourth is I squared times I squared. And we know that the I squared is -1. So -1 times -1 is 1. So it cycles through and it actually gets us a 1. 1, remember, being the god of mathland. He, she, it is with us whether we see him, her, it, or not. Well, what does that mean that I to the fifth is going to be? Well, I to the fifth can be I to the fourth times I, right? Because when you multiply like base numbers, you add the exponents. 4 plus 1 is 5. And I to the fourth is 1, so 1 times I ends up being I. So I to the fifth is just I. I to the sixth, then, is I to the fourth times I squared, which would be 1 times -1, which is -1. Well, look at that. I to the sixth is the same thing as I squared. I to the seventh is going to be the same thing as I cubed, which is -1. I to the fourth is going to be the same thing as, I to the eighth is going to be the same thing as I to the fourth, which will be a +1. And then we cycle through it again. So when you're dealing with powers of I, you only have 4 choices. You either have I, -1, -I, or or 1. Those are all of your choices. So here's the neat thing. It spins around those same 4 choices over and over and over again. So if you think about those values being like numbers on a spinner, and you spin it around, zzz, we just want to know which one it ends on. It doesn't matter how many times it cycles through that group of 4. In order to find that, what we can do is we can take our exponent. So if I want to find out what's I to the 37th, well, we could go through and say, okay, 1, 2, 3, 4, okay, then 5, 6, 7, 8, and we could count around our circle until we hit 37 and see which one we land on. But because there's only this group of 4, I can divide out, because this is really just cycling around. I can get rid of all those full circles. What matters is where I end. So to simplify this, I can take that 37 and I'm going to divide it by 4. Because I have 4 options here. That was 9 times 36. And then we'd go big R1, right? Long division back in the old school, big R1. We don't care how many times we have that we've spun fully around. We care about where we end. So I to the 37th is going to be the same thing as I to the 1st, which in this case would be just I. If I had I to the 47th, take 47 and divide it by 4. Big R3. So I to the 47th would be the same thing as I cubed, which is negative I. So I to the 47th is negative I. So if you have a remainder 1, it's going to be here. If you have a remainder 2, it'll be a negative 1. If you end up with a remainder 3, it's over here. And remainder 4, well, if you're dividing by 4, you don't have a remainder 4. So no remainder. Gives us a result of 1. So I could literally ask you, okay, find out what I to the 256th is. And all you'd have to do is take that 256, divide it by 4, and find out what your remainder is. Now, if you're not good on your long division and you're going to use your calculator instead, a remainder of 1 is 1/4, so you'd have a decimal of 0.25. That would be the same thing as remainder of 1. Here, when you divide it out, you'd have a decimal of 0.5. Here it would be 0.75. And again, no remainder means that you don't have a decimal point. It divides it evenly. 256 is divided by 4 evenly. So I to the 256 is really just 1. So that's kind of a neat little thing to go off of there. You can find out the different powers. So we now know how to add, subtract, multiply, do a little division with our imaginary numbers, and then simplify higher powers. Hopefully this helps.